In this video, we are going to talk about topic 5 in Unit 1, which is statistical graphs. Once you've collected your data by performing a sample, an observational study, or an experiment, you're going to have a big, long list of data. And remember, data can be yeses or nos. It could be numerical measurements, but it's just going to be some big list that if you were to look at it on its own, it wouldn't really have a lot of meaning. So the first thing that you want to do is describe your data. There are two major ways that we are going to be doing this. We're going to be using graphs, which is what we're covering in this topic, as well as numerical summary measures, which is what we're going to be talking about in topic 6. Both of these overall are part of descriptive statistics, which is the step after you've collected your data when you begin to describe it. So definitely the first thing that you want to start with is graphs. There are two major reasons for this. First of all, it's going to reveal typos very often, and this is something that happens way more than you would think. I have this happen to me on a pretty regular basis. So when you're entering in your data, that's not always something that you are paying a lot of attention to. It's really easy to make typos. The second reason, of course, is that so you can really get to understand your data set and start to get an idea of what it looks like. Because again, a big list of numbers is very difficult to understand on its own. One of the downfalls to making a graph, however, is that you very often will lose your original list of data. So instead of having, for example, if you had test scores, you don't have the physical numbers anymore. You may just be using things like mean and median, which we'll talk about in the next unit as well. So you might actually lose some of your original data. There are a lot of different types of graphs. Some of them are very popular and they range to very, very specific types of graphs that are really specific to the field that they are in. The more popular ones that we are going to be talking about are dot plots, stem plots, bar graphs and histograms, box plots, scatter plots, and multiple bar graphs. Some less situational ones that I do, or less popular in situational graphs that I do want to bring up because it is important to acknowledge there are other types. Sometimes if your data is specific, you might need to research a type of graph that you've never heard of before. So some of these less popular for us are pie charts, Pareto charts, frequency polygons, ogives, and time series graphs. We are going to be using software as well to create these, but when we first go through with this section, we're going to be thinking about the making these by hand. And then when we get to our lab activities and learning quizzes, we will be potentially making these graphs using Stata software. So first is a dot plot. And a dot plot is a graph where each value is plotted as a point or dot along a scale of values. Dots representing equal values are stacked, and the bottom axis is a number line. So let's look at an actual example for this. So this is an example of a dot plot for categorical data. So along the bottom, this might be M&M colors. I don't think it would be favorite colors, just my guess. So each dot in this case is going to represent one person or one M&M, let's say. So if the dots were representing 5 or 10 or even something like 7, which would be less common, but it could technically be done with 7. If they were a different count amount, then there would be some kind of label on the side. So if I were to read this dot plot, I would say, okay, there was 3 blue. Let's see, 3, 6, 9, 12, 15, 18, 19, 20 brown, and so on. So I'm just counting the number of circles, and that corresponds with how many, the frequency of that color that there were. Next, this is an example of a dot plot for quantitative data. I would assume lead average. So I would assume that this is the average amount of lead in water or some other kind of material. So this bottom axis, since it's quantitative, is a number line, and it is most likely continuous because we're assuming that we're measuring this type of lead. So each dot that is stacked could represent, one sample that had that amount. Not all graphs are good ones. I actually included this one because it is a little bit cluttered. It does make it difficult to read specific values. So this is a dot plot that if I looked at it, I would actually say, hey, we either need to improve this dot plot or maybe even consider using a different type of graph altogether. But dot plots are very, very good for continuous data because when you measure, you're going to have to cut it off somewhere. So dot plots are very good for, I think, any kind of data. And they're pretty self-explanatory too, is one thing that I like about dot plots. So I have an example here. Dot plots is one of the ones that I would like to have everybody imagine they were making by hand at least once. So I have an example here that's going to represent test scores, which we'll see in the next slide. And there is already a dot plot that has been created and set up. So now suppose after this, there are 7 more test scores that were reported. So what I would like you guys to do between this slide and the next is to place where each of those values would go inside the dot plot. So I would pause here and at least if you don't do it physically, just kind of maybe tap your screen as to where you think that these values should go. So the solutions for this example, these 6 numbers as well as the label axis are what we would want to add to the dot plot that was already existing. So first, test scores, I put those along the bottom. You want to label every graph as much as you can because the goal of a graph is to make your data presented in a way that it is as easy as possible for someone else to look at and understand. The more questions that they have that are specific to reading your graph, the less likely that your graph is doing a good job at what it should be doing. So we have 7 points here. 70 is the red dot, so I did color coordinate them. So the red dot that is stacked above the 70, so you want 2 things to happen when you add in these dots. The first is that you want the count of 2, so my second dot here, to be on the same height as the other dots that represent the count of 2. So you want it to be even, both in height as well as spread going across. So this dot right here is a little bit shifted to the left, but the rest of them are good. So this one, when I looked at this, I kind of felt like it was a little bit off. And sometimes you need to see it with a little bit fixing that needs to be done in order to truly understand how it should be created. So the second 2 dots are 62s, so those are going to be stacked right above where the 62 would be. So as I read the bottom axis, this height right here is going to represent scores of 60. It looks like there was no students that had a 61, and then we have 3 students now with a 62, and so those are going to be stacked on top of where the 62 would go. The next score is a 64, so that is going to take this from a height of 3 to a height of 4, so that's again right before where the 65 would be. 85 is going to be up here to the right. There already was one 85 and now we have a second. 93, very similar. So some of these are in the middle of the tick marks and some of these are on the edge, and that's just to get an idea of the way that the bottom axis is working. So this would be 90, this would be 91, this would be 92, and then this height right here would represent 93. Lastly, we have a kind of an oddball one here, 47. So this is way down here to the left. It is in between 45 and 50 for sure. So 45 would have a stack here. 46 would have a stack here. So this is our first 47. So it's important to make sure that you line things up both height-wise as well as horizontally. The next type of graph that we should look at is a stem plot. Stem plots are also known as stem and leaf plots, most likely is probably how you would know them. And a stem plot is a graph that represents quantitative data by separating each value into 2 parts, a stem and a leaf. Very often, a stem is the leftmost digit and the leaf is the rightmost digit. However, the more and more digits your data is, the more complicated it will be to create a stem plot. So my general kind of my mantra about this is that if this stem plot is really difficult to make, it's probably going to be more difficult to read, and maybe you should consider a graph that's different from stem plots. There is a sample stem and leaf plot on the slide. So the numbers range from 15 to 41. And so the stem in this case makes the most sense to be the tens place. The leaf should be the ones place. So ideally you separate the bigger ways to break down the number with the smaller ways, like the tens and the ones. So if we were to take this data, the 15 through the 41, and put it into a stem plot, we would have the stem and leaf plot below. So 15 and 16 is what this first row would represent. So that corresponds to the 15 and the 16 that we have above. We have a lot more in the 20s, so this stem and leaf goes longer on this row here. So 21, 23, 23, 26, and 26. You do want to have two things. You want to have them be equally spaced, which these are decent but not perfect. You want them to be equally spaced, and you also want them to be from low to high, both in your leaves as well as your stems. So 30 and 32, this isn't very easy to read, but the highlighted numbers all go together for that 32 up there. And then lastly, we have 41. So on this slide, make a stem and leaf plot for the following quiz scores from a math class. Label your stem and leaf. So when it says label your stem and leaf, you want to label with what digit they are representing. So take a minute, pause the presentation, and complete your stem and leaf plot. So the solutions for the stem and leaf plot, I labeled the stem as the tens place, the leaf as the ones place. It's very important to recognize that the stem and leaf are not always going to be tens and ones. A lot of times the stem could be the tens and ones, and the leaf could be the tenths place. But again, the harder it is to make a stem and leaf plot, the more likely it is that the person reading it is going to have a difficult time. So if you take these stem and leaves and compare them to the values before, and also they're even. So the 613031 in the column for the first leaf, those are all perfectly even with each other. So the farther of a distance you get to the right for your leaf represents the more numbers there were with that stem. So you want to make sure that that is consistent as possible. So the next type of graphs that I want to talk about are bar graphs and histograms. These are very, very similar graphs. They're often confused, but there is a technical detail with histograms that's really important to adhere to every time. So that's why I put these together, because the comparison of the two helps you understand them. So a bar graph, it uses bars of equal width to show frequencies for categorical data. The bottom axis has the categories, and the height of each bar represents the count for each category, so just how many of that there were. There are an equally sized space between each bar, and the bars themselves also need to be the same width. So for a histogram uses bars of equal width to show frequencies, so same things to counts, but for quantitative data. The bottom axis is a number line. The height of each bar represents the count for each category, which in this case is going to be a span of numbers, and there is no space between each bar, and we will talk about why that is in the following slide with our examples. So on this slide we have two examples. The left example shows a bar graph, and the right example shows a histogram. So the left example is a bar graph because the bottom axis has categories, and that's one reason why it's okay to have spaces in between each of the bars. So in between red and orange, orange and the yellow, there's an equal sized gap there. The height of each of these, so the red goes up to 35, so that means that there are 35 apples. So the height of each of these represents how many there are. For the histogram, there is a minor problem here. So again, sometimes you need to see one that's a little funky in order to understand how to recognize it. So this histogram is the 31 NFL team salaries. So I'm not completely sure about the nature of this original data here. But each of these bars, again, represents a count. So I would assume the purple one is probably 13. And each of these should be equidistant. And they all look pretty good, except for this first one, the red bar, and then the last bar, the pink bar. So you want them to be equal sizes and as far as distance in the number line so that you can easily compare one bar to the next. So this is actual correct information, but the bars were just made a little bit too large. So the next major type of graph that we're going to be looking at is a box plot. Depending on your data, you may have a single or multiple box plots. So a box plot is a graph created using the 5-number summary, which we will talk about in a few topics. And the 5-number summary is the minimum value, the maximum value, and what we will learn are quartiles. This is an example of a single box plot. So this is a box plot that represents a single list of data. And so this example I just got from Google Images, and it is Mrs. Sanchez's period 1 math quiz results. So there are different variations of this. Sometimes you may have a straight up and down line at the 20 and the 94. Other times you may have a dot at the end. So when we get to this specific type of graph in the later section, we'll talk about those specific details. One thing you'll notice with this data compared to something like a dot plot or a stem plot, for example, is that we no longer know the original numbers. So we don't know how many numbers there were. We do not know what the numbers exactly were. We just have lines. This is one summary measure. This is another, and this is going to be another measure of summary. So this, as well as with histograms, we don't know the original data any longer. We're just now starting to summarize it. And this is okay. Sometimes this is actually a good thing, because if you have, 1,000 numbers in your data set, you don't want to have 1,000 dots in a dot plot, but you do want to have a really nice, clean way to view the data in a graph. In this slide, we have a multiple box plot. So one thing about this box plot visually is that along the bottom, those labels do kind of collide into each other. So this is something that when you produce a box plot, you want to avoid. And also up at the top, the title is cut off a little bit. That one was less intentional than the labeling along the bottom. So the axis on the left, the vertical axis, says billion tons of oil equivalent. So basically this box plot, multiple box plot, is to compare the different energy sources. The dots that you have for oil and renewable, those typically represent outliers. So this is again one variation of box plots that you might see, but we don't cover box plots formally in this topic. So that's why there's so many general details about box plots right now. Scatter plots are really popular, and these are ones that students are usually pretty familiar with at a general level. So with scatter plots, you are making a plot, an XY pair, of quantitative data. So in this case, our X, our horizontal axis, is our education level, and they would have done their background research to describe how they're going to summarize education levels. So I believe this is older data, and I do believe that this is from data that wasn't in this country. So that's why 6 to 16 as far as education levels don't make sense. So this is an example where we would need a little bit more information here on our bottom axis in order to be able to make complete sense of this. This type of graph is not going to be covered in detail until actually Unit 5. So this, again, the goal of this section is just to really understand the goal for making graphs as well as all of the different types that you can make. Income level is on our vertical axis, and so this is 0 to 25,000. So maybe these are students. Maybe this actually is a sixth grader. But again, the graph itself doesn't give us enough information to understand exactly how those labels are being used. So this graph is correct, but it needs stronger labeling. Our last popular type is multiple bar graphs, and this is where two or more sets of data are displayed for each category. So this is really good for categorical data. It's the same thing as a regular box plot, except for we may be tracking more than one thing for our categories. And in this case, we are looking at Lisa's collection of music and books. So over time, we see that in general, we have a growth for books, a growth for music. So it looks like maybe she's getting a bigger budget here. And then originally, books is a pretty big difference with CDs. And over time, not only does the gap in between them decrease, but we eventually get to where books is actually higher than music CDs. This is something where if we had a regular plain old list of numbers, we wouldn't see this relationship as clearly as we do with a graph. So a number of the less popular or situational types of graphs, pie charts are going to be pretty commonly known. I'm not saying that a pie chart isn't a good graph. A pie chart is perfect for when it is applicable. So a pie chart is a circular graph for categorical data where the size of each slice is proportional to the frequency count. So 100% is going to be the whole entire circle here. So this is 100% of our movies that we've collected. And the size of each slice corresponds with the number of people that responded with that category. So we have favorite type of movie with this one. And the biggest slice is romance. So this is where I would say, hey, what kind of sampling method did you use? Because, maybe you tended to get, maybe more women is what I would think if you want to believe this stereotype here. So drama, we only have one. It's the smallest count, and it's also the smallest slice of pie. So the shape and size, not shape, but size, does equate to the count of people that responded with that category. Next, we have a Pareto chart, which is actually a specific type of bar chart where the bars go in descending order. So this would not work for a histogram because a histogram has a number line on the bottom axis. And it's very important that the bottom axis stays in order, just as the number line does. So originally they may have had this in a very different order. Maybe delivery was the bar that came first. And then the person that created this graph thought, hey, maybe it would be easier for a person to read if they saw what was the highest count and what was the lowest count. So again, this is just a modification that you might make depending on how you want your graph to be read. So next we have a frequency polygon. I personally have not ever made a frequency polygon. However, that does not mean that you may encounter a data set where a frequency polygon might work or might not work for it. So this is lines that connect the midpoints, so the middle of histograms. So this would be something that came from a histogram. It would need to be continuous data, but we're just going to mention its existence, so we understand, hey, there's a lot of different types of graphs, even if we don't discuss them in this class or this topic specifically. Next, we have an ogive. This is actually a graph that I see pretty frequently, and it's usually on my cell phone bill. So an ogive is a graph of cumulative frequencies. And I usually see this on my cell phone bill, specifically when I'm checking my data usage. So data usage, they usually like to show over time how you're reaching your maximum amount of data you are allowed to be using. So a lot of times people look at an ogive and they don't think that it would be something that they would want to use, but it is something that you definitely see more often than you think. So the line is always going to be increasing over time because cumulative takes what you have previously and adds to it. So this is something that for our first lab activity, I will give you an example of data usage for my cell phone bill. So we'll get a chance to see a specific one of these. Next, we have a time series graph. This is definitely not a less popular type of graph, but it is very specific. So for that reason, it fell in this category here. A time series graph is a graph of quantitative data over time. Many times you are interested to what happens over time, just like Lisa's music and CD collection. So this is real data that I obtained from Google Trends, which we will see occasionally. And this is the Google searches for snowboard and the Google searches for surfboard over time. So we're going to see two things. We're going to see a trend specifically over time for snowboarding and surfboarding separately, and then we also want to look at the two of these together. So if you think about it, the reason for a pattern that is opposite for the blue and the red, the snowboarding and the surfboarding, is probably because of the seasons. So the big peaks for snowboarding, I would assume, are winter, and the peaks for the red, I would assume, are surfboarding in the warmer seasons. The other thing that you may notice is that originally surfboarding and snowboarding are a lot higher in the Google searches, and they do in general decline over time. So there's a lot of different ways that you can analyze a graph like this. You can look at the individual as well as the comparison between the two, which in statistics is a lot of times what we do want to do. And it is more interesting usually than a data set all on its own. So this is the end of our examples for statistical graphs. Again, there are a lot more graphs that we will encounter. It's just that they tend to be more situational than not. The major ones that I would like you to take with you from this section are dot plots and stem plots. For now, those are the types of graphs that retain the original data, which means we don't need to have specific summaries from our next topic to do.